Chapter 22, it's a big one, I'll tell you right now, magnetism. Let's take a step back and think about what we've done, most importantly, and how that relates to magnetism, and that's the electric field. For me, this course is about the electric field and the magnetic field. So we've looked at the electric field, we looked at if you have a charge Q and another charge Q over here, they repel each other with some force. We can describe that force as the charge Q times the electric field created by this. So whenever you have an electric field E and you put a charge in there, you get a force Q times E. And I'm writing that as a scalar version because that's how the textbook does it. Yes, this is OpenStax Chapter 22, College Physics. Okay. So, that's what we need to know about electric force. A charge makes an electric field, and a charge in another electric field experiences a force. That's a big deal. Now, let's talk about the magnetic field. I'm going to write it out. B. Where you're going to use B for the magnetic field. So that's the third field that we've seen. We've seen the electric field E. We've seen the magnetic field B. And then in your previous physics course, you saw G, the gravitational field. Okay, they're all force per unit. This is the force per unit charge, force per unit mass, and this is a force per unit charge velocity. Let's just talk about magnets for a second because there's some really awesome things here. I have one magnet right here. Where'd my other magnet go? I had two. Oh, here it is. So if you haven't played with a bar magnet, here I have two bar magnets, and you can see that when I bring two ends close to each other, they are attracted. So we can describe each bar magnet as having a north pole and a south pole. And so if I have a north pole and a south pole, they attract. If I turn this one around so that I have two north poles, they repel. And if you haven't played with that, you should because it's a lot of fun. I don't know, it just feels cool. It turns out that if I take this bar magnet and break it into two, I'm still going to have a north and a south pole. The north and the south pole aren't real things. They're not charges. Okay, in the same way that a charged tape or a charged object has an electric charge on it, this is not the same thing. It's different. But we can kind of treat it as though it were the same, especially when you talk about permanent magnets like this. Now, I do want to talk about a couple of important permanent magnets. Here is one. This is a compass. This compass needle is a magnet. It's a magnet that can rotate. And you'll see that as I bring this other magnet near it, nothing happens. But it should. There. It's not working because I'm holding it vertical. It's supposed to work like this, okay? Normally this works by having this magnet that's movable interact with another magnet, and that's the magnetic field of the Earth. The Earth acts like a giant magnet. So let's get our Earth model. Some people call this a globe, but it's a model of the Earth. Okay. So if I have my compass right here, the north end of the compass points up here, the North Pole. But that's because this is the south magnetic pole of the Earth. Imagine the Earth is a magnet, this would be the South Pole, and this is the North Pole. So we call that north because that's the direction the North Pole of a compass points, even though it's a south magnetic pole. I know, it's weird, but we kind of decided these things before we really know what's going on. Now, I do want to tell you something while I have the globe. There's a couple of really cool things that you can do with the globe. Fun trivia questions. Let's start with the one that's most important. Here we have the Arctic, right? Up here, that's the North Geographic Pole. And then that, there it is Antarctic. Antarctica. Arctic, Antarctica. So what do those two words mean? So the North Pole, the Arctic, this is true, okay, you can look it up, means bears. This means down here, Antarctica, no bears. Because there's polar bears up here, there's no polar bears down there. It's true. I don't know. Okay. Enough about bears. Let's get into the magnetic force. Things are going to start getting a little complicated, and it's not because of that we want to. So let me just remind you here. Here's an electric field. There's a charge. F equals QE. I'm going to write it as a scalar, even though it's technically a vector. Now let's suppose that I have a magnetic field caused by something. We'll get into it in a little bit. I'm just going to write it B, although it does have a direction. I've already shown the direction. And I put a charge Q there. There is no force. Charges do not experience a magnetic force. However, if that charge moves with some velocity, and I'll actually write this as QV, right? Because if it's a negative charge, QV would be in the opposite direction. So it's important to group those together, QV. Then it does experience a force. We can calculate that force very similar to this as QVB sine theta. So Q is the charge in the field, V is the velocity, B is the value of the magnetic field, and theta is the angle between, is that between, or is that B? Oh, that's fine. Between B and QV. So right here you see with the way I drew it, the angle between B and QV is what? The answer is 90 degrees. It's a 90-degree angle. The sine of 90 is what? The answer is 1. The sine of 90 is 1. If I had another charge going this way, the angle between QV and B would be 0. The sine of 0 is 0. So there's no force acting on this one. There is one on that one. That's how we'd calculate the magnitude of that force. But what about the direction? Here comes the tricky part. The right-hand rule. Right-hand rule. So we can determine the direction of the magnetic force on a moving charge, 1, by saying it's perpendicular to B and QV, and 2, using the right-hand rule. Okay, so let's draw some vectors here. So here's my QV. I'm going to just draw it like that, and there's B. Okay, those are easy to draw. If I want to pick a vector that's perpendicular to both of these vectors, there are only two. There are only two vectors that's perpendicular to QV and to B. One of those vectors is this, a vector coming out of the board, right? If I have a vector coming out of the board, like this piece of chalk, it's perpendicular to B, it's perpendicular to QV. So we describe a vector coming out of a board as a dot with a circle around it, because that would be like an arrow coming straight towards you and you just see the point. The other vector that could be perpendicular to both of these is this, a vector going into the board. And when we draw an X with a circle, that's an arrow and you're looking at the back of the arrow because it's going away from you. So that's the two options that we have. It's either, in this case, it's either out of the board or into the board. And then we use the right-hand rule to determine which one it is. So with the right-hand rule, it says take the fingers of your right hand, and if your fingers cross through QV, and then B, that tells you the force. So if I go this way, see my fingers are going through B and then QV, and my thumb is pointing into the board. So that's not it. If I go from Q this way, I cross QV and then B, and I get that. So this is the answer. It's not that one. So that's how we use the right-hand rule. Now, let me give you a really useful version of the right-hand rule. Let me grab a, I'm not prepared for this. I wasn't prepared. Fine, I'll just use this. So this is a screw, we traditionally use right-handed screws. So a right-handed screw is if you take your right hand and turn in the direction of the fingers of your right hand, the screw will go in the direction of your thumb. So if I take this and I turn it this way, then the screw goes down, right? And if I turn it this way, it goes that way. So it's coming out. This is super useful. Yes, I know you could say righty-tighty, lefty-loosey. I get that. But when you're like looking at something underneath, it's kind of hard to say which way is righty mean. That doesn't mean anything, okay? So instead, you can use your hands like this. Oh, I want to screw it in, then I'm going to have to go this way. I want to unscrew it, I want to go that way. Now be careful. There are left hand threads that do the opposite. They use your left hand and go, that's the way you'd unscrew it. So some things like gas tanks, bicycle parts. I have some scuba gear where the threads are reverse threaded to connect two tanks. So there are those cases. But in general, right hand rule. It has nothing to do with the magnetic field, but it has everything to do with the right hand rule. I made this. So because we are inherently a 3D problem, it's hard to visualize the directions of all these things. So here, just to show you what I mean, here I have QV, the direction of Q, there's the vector B, and then that would be the direction of the magnetic force. And so you can rotate this around in any direction and it's still true. Now, also, I should point out that these don't have to be perpendicular, okay? So we could have a situation like this. B, QV, okay? So they're not perpendicular. This doesn't quite work, but you can still get the idea. It still mostly works. I can still put QV like that, and then B would be kind of like that, and it'd be a magnetic force would be into the board. I have to tell you, there is one other version. There's a whole bunch of right-hand rules, okay? There's another one that you'll see that looks like this. And this is the same thing. See? So if I put my finger in the direction of QV, my middle finger in the direction of B, then this will be the direction of the force. Okay, that's enough. Okay. Oh, B is in the electric field is in units of newtons per coulomb or volts per meter. They're the same thing. The units for the magnetic field are in Tesla. We just say T. Okay, let's look at two examples. There's a bunch of awesome examples, but we're just going to look at two. And again, remember, these things are hard to draw. I might make a second video using the images from the book just so we can talk about a bunch of stuff. But suppose I have a magnetic field, and I'm drawing it like this. This is a magnetic field going into the board. So I'm drawing the X's with the arrows. Now suppose I have a positive charge with a velocity going that way. So this is Q. If that's the case, what direction will this charge experience a force? Well, I know that QV is that way, B is into the board, right? So it's either going to be this way or that way. And now I can use the right-hand rule. If I do QV cross B this way, it tells me the force is that way. So it's not that way, it's that way. And it's perpendicular to the velocity. So what's that going to do to this particle? It's not going to make it speed up or slow down. When you have forces perpendicular to the velocity, it makes it change direction. So a little bit later, it's going to go over here, and it's going to be going this way. So now QV is that way. Which way is the force now? You can use the same right-hand rule, and you'll find that it's that way. That's going to make it change direction again. It's going to do this. It's going to keep pushing it into a circular motion. So a particle in a constant magnetic field, if you shoot it perpendicular to the field, it's going to make a circular motion. Now, we can actually use our ideas from the previous semester to find something. So here's my circular motion. Here's my particle. It's moving that way with a velocity qv, and it has a mass m. And this is the radius of the circle r. So I can say that at this particular moment, F net, the magnitude is QVB, right? Because they're perpendicular, Q, V, and B are perpendicular. Sine of 90 is 1. And that's going to be equal to, wait for it here, mv squared over r. Where did that come from? Well, F net is mass times acceleration. And when an object moves in a circle, it has an acceleration of v squared over r. I bet you thought you were going to not have to remember that from the last semester, but there it is. Okay. So with this, I could actually solve for the radius of the circular motion. Notice right here that one of the v's cancels. And then if I divide by qb and multiply by r, I get r equals mv over qb. This actually has some important applications. One of the things that I'm not going to really look at right now, I'm going to tell you, is what's called a mass spectrometer. You take a particle and you shoot it into a magnetic field, and if you know the velocity, you can see where it bends and where it hits some detector, and the size of the radius that it bends in depends on the mass. So you can determine the mass of those particles. You have a mixture of a bunch of stuff, you take it and you shoot it in there, and you see what happens. Okay. My camera's not messing up because I didn't get mad. Let's see what this is. Okay. So you're not messing up. Okay. Okay. Let's look at another really crazy application of the magnetic force. And this is called the Hall effect. And you use the Hall effect all the time to measure magnetic fields. But suppose that I have a wire. And I apply an external magnetic field onto that wire, going into the paper right here. And so this one, let's say we have a current going this way. The current's going that way. Now, do I have moving positive charges or negative charges? You know, a lot of times we say we can't tell the difference, but you can tell the difference, and here's how. Okay. So let's say that I have positive charges. So a positive charge, and in order to have a current going that way, I'd have it moving this way. Well, now I have a moving charge in a magnetic field. What direction would the force in that be? Well, there's two options, right? It has to be perpendicular both QV is that way, and B is that way. So it's either going to be up or down. Now I can use my right hand rule. When you're right-handed, and you do the right hand rule, take out the pencil. Okay. If you're left-handed and you use the right hand rule, don't take out the pencil or pen or chalk. Okay. So now I'm going to let my hands go through QV and then B, and it tells me that way. So the force on that positive charge particle is down, and so what's going to happen is that I'm going to get these particles are pushed to the bottom, and I'm going to get positive charge down here. That means that since the wire is overall neutral, I'm going to get a leftover cores up here that don't have positive charges. So I'm going to get negatives up there. So I'm going to get a charge separation. So this charge separation, I can then measure the change in potential. I can put a voltmeter up there and measure that. And if this has a length L, I can even calculate the value of the electric field. So the electric field, if it's constant in there, would be down, would be up. And it would have a magnitude of delta V over L. And now it's important, because imagine that I have this electric field. Now my charge has two forces acting on it. There's the downward pushing magnetic force, but now there's an electric field too, and it's going to push up on it. So eventually these charges are going to separate to the point where there's a charge here. I have a downward magnetic force FB, an upwards electric force FE, and the net force is 0 and just moves along like it did before. Okay. So the point is, this is called the Hall effect. So the point is, you apply a magnetic field, it's going to cause this charge separation on the wire that you can actually measure. You can measure that change in potential. Now let's repeat the experiment. Same magnetic field. I'm just going to put X's. But now I have a negative charge carriers, and they're moving that way. I still have the current is to the left, right? If the current to the left, that'd be negative charge is moving to the right. Now if I do the same thing, now I have QV. There's V. But QV is still this way, right? Because it's a negative charge. So I still get the force being down. But now they're moving negative charges, so I'm going to get these negative charges down here, which is going to leave positive charges up there. So that's how we know that in a wire, it's the negative charges that move, because we can tell the difference between negative charges up here and positive down here, or positive up here and negative down there. And that's the whole effect. Now, we can actually reverse this. You can take a device like this, apply a magnetic field. The greater the magnetic field, the greater the charge separation. Calculate this voltage and use it to determine the magnetic field. So your phone probably has a magnetic compass in there, and you can say which way is north, and it does this. Okay, because you want to have an actual compass in your phone because you want it to be as small and thin as possible. Okay. Moving right along here. But the important thing here is that the change in potential. The change in potential, we know the electric field has to be equal to the electric force has to be equal to the magnetic force. So I can say this: QE is QVB in this case. So the VB. So let's find E. So E is going to be equal to VB. And then the change of potential, delta V, is going to be the electric field times the distance. So I get delta V is VLB. This is an important thing, and it shows up in a lot of different places. We call this an induced potential difference due to a magnetic field. So if you're moving in a magnetic field, it's effectively that change of potential. This is hard stuff. Okay. If you're confused, it's okay. We're going to do some problems later and so forth like that. So we have the magnetic force on a moving charge. I'm going to call it FB. QVB sine theta. Please don't stop me. We're still good. My phone, it's kind of like pauses stuff. I think it's okay. I'm going to keep going. Don't make me start over. Okay. But what if I have, instead of QV, I have a wire with a current I? And I apply a magnetic field over there. I can make this a force on this wire, and the force on a wire carrying current is also a magnetic force, but instead of QV, I get ILB sine theta. So that's the current in the wire, that's the length of the wire, that's the magnetic field, and again, we're looking at the angle between the direction of the current and the magnetic field. This is pretty important, because if I can exert forces on a wire, then I can do awesome things like make the wire move. One very useful case is with an electric motor. And I need better pictures here, but I do want to just show you that a loop of wire, the net force on a loop of wire is 0. So in a constant magnetic field. So let's say that I have this. So here's my wire carrying current. It's in a magnetic field like this. And so this is a length L and a width W. Okay, so these two parts right here really close together. I can consider this as 4 wires moving in 4 different directions. So let's start with the top wire. What's the direction of the force of the top wire? Well, we still use the right-hand rule, right? So magnetic field's in, IL is that way, so it's either up or down. I'm going to use my right hand and let it cross through IL and then B, so I get, this is the magnetic force, FB. Now let's do it over here. Again, the thing we're going to do, IL is down. I can use my right hand rule, cross it into B. I get it this way. If you make one of these, a smaller version, it's a great thing to have with you when you're doing homework. It doesn't have to be that big. And then you can kind of say, okay, IL is that way, B is that way, the force is that way. See, I even put that force. Down here, IL is that way, FB is this way, and over here, FB is this way. Now, you'll notice that the length of this wire is the same as the length of that wire. So this force is going to be equal and opposite to that force, so they add up to 0, and the same thing over here. No force. So there's no net force on the wire. Okay. Now let's say that we have my wire, and I have the magnetic field going this way. Okay, let's do it again. There's IL. What's the force on this wire up here? Well, now we have a problem, right? Because I and B are in the same direction, so there's an infinite number of vectors perpendicular to those, and the angle between them is 0. So there's no force on that wire, on that top part. F equals 0. Down here on this bottom part, the current's going this way. The angle is 180 degrees. Again, the force is 0. What about right here? Now I have I going down. B is that way. So what two forces would be perpendicular? It would be either out or in. So if I use IL, I is that way. B is, I'm going to do the C. I can confuse myself. Okay, so yeah, I want to do it like this. If I cross this way, right, I'm going to cross into I and B. It's going to be out of the board. If I did this, it would cross B and an I. I don't want that one. I want this one. So this one's going to have a force coming out, F. What about over here? Now, IL is going up, and B is that way. So I do my right-hand rule. I get this way. No, I get into the board. Like that. So the length of this wire, the length of that wire is the same. The magnetic field is the same. So these two forces are equal and opposite. Those are 0, equal and opposite forces. So also, no net force. However, imagine that I have this wire and I push down right here and I push up right there. Although the net force is 0, it could make it rotate. There will be a torque. So if I calculate the torque about the center, and what did I call this width? So this is W over 2. So the torque is going to be the torque due to that, which would be the torque arm, W over 2, times the force, which is ILB, sine theta, but theta is 90 degrees. And then the torque arm here is in the same direction, right? Because now the force is that way, but it wants to make it rotate the other way. So I get W over 2 ILB. Add those two together, and I get IWL. I did that for reason B. So W times L is, and technically this would be, well, yeah, that's the area. So the current through the loop, that's the area of the loop, that's the magnetic field. And so here, that same situation, we had 0 force and 0 torque. Right, there's no torque on this one. Here we have 0 force and a torque of ILB. It turns out that in general, as you rotate between those two, you get torque equals I, A, B, sine theta, where theta is the angle between the normal perpendicular to the area and the magnetic field. I don't, that's complicated, you need to picture it, but there is torque on a wire. Why would you want torque on a wire? This is an electric motor. Okay, this is how we make an electric motor. You have a coil of wire with current running through it. You apply an external magnetic field. There's more than one way to do that. You could use permanent magnets, and you can get the thing to rotate. Now, in order to make it keep rotating, you're going to have to switch the direction of the current, and that's one way to do that is with these things called brushes. I'll show you a demo of that. I promise that I will, but I want to introduce it to you. It is pretty complicated. That's the motor. In general, it could also be, we actually should write this as torque is in IA, B sine theta. So in this case, N is the number of loops, because you're not just going to have one loop. In order to make a better motor, you want to loop it around a lot of times. Okay. It's still recording, right? Yeah. Okay. Let's see, what do we have next? Now we've looked at forces on moving charges, forces on wires due to magnetic field, but we didn't say how you make a magnetic field. Well, it may not be a surprise, but if a moving charge experiences a force in a magnetic field, a moving charge also makes a magnetic field. So the easiest way to find, there's a lot of ways to do this, but in general, if I have a wire, I'm going to draw the wire coming out, the current coming out of the board. It's going to make a magnetic field that makes a circular pattern. This is V. And the further away you get from the wire, the smaller the magnetic field. We can calculate that as mu naught over 4 pi, what is it? I over R. No, it's 2 pi. So mu naught is just a magnetic constant, just like K was the electric constant for electric fields. I is the current, R is the distance from the wire. And then we can use our right hand to determine the direction of the field. So in this case, if you take the thumb and you put it in the direction of the current, it shows you the direction of the magnetic field that goes around circles. And that is kind of important. We'll do some problems with that later, though. It takes practice. If I have a loop of current, I can find the magnetic field in the center of that. It's just going to be equal to mu naught I over 2R. And so a long wire, magnetic field, a loop. And then finally, if I have what's called a solenoid is a bunch of loops. This on the inside makes a magnetic field that's very constant. It's the capacitor version of the magnetic field. And here B is equal to, why can't I remember this? It's just mu naught N I, where lowercase n is the number of turns per length. So this would be a total number of n and the length L. N would be N over L. Whew. Okay. There's a bunch of applications for magnetic fields. I will try to make another video, at least with some demos. So, and I think I made it through without too many hiccups in the video. Double thumbs up. Come on. There we go. Okay, the end.